The universe was once thought to be small. By the 1950s, astronomers already knew other galaxies existed beyond the Milky Way. But all that space seemed manageable, just a few billion light-years across. This view masked something that could rewrite the laws of physics, and the first clue didn't come from an observatory. It came from the lab of an engineer who simply wanted to eliminate crackling from a telephone line. A few billion light-years sounds vast, until you realize the actual observable universe is about 30 times larger. It's like if the people of a tiny island nation honestly believed their island was the entire land on the planet. Beyond the shore, there was only water and nothing else. Astronomy in the 1950s stood in roughly this position. Galaxies were discovered, space was proven to be expanding, but the scale of that expansion remained a mystery. The cosmos felt compact, comfortable, and completely safe. Now for the strangest part. The signal that this cozy world was just an illusion arrived 20 years before anyone even noticed it. It's 1931, New Jersey, rolling hills just south of New York City. An engineer named Carl Jansky works for Bell Telephone Laboratories. His job is straightforward: track down the source of static in transatlantic radio transmissions. Crackling, hissing, noise. Everything that ruins the clarity of voices on the other end of the line. Routine stuff. A technical problem with no connection to the stars. Jansky built a rotating antenna, a bulky frame made of wood and metal, mounted on wheels from an old Ford. It turned slowly, completing a full rotation every 20 minutes, capturing signals from every direction. He quickly identified 3 sources of interference: nearby thunderstorms, distant storms, and something else. A faint, steady hiss that never vanished, day or night. It didn't depend on weather or power lines. It came from the same spot in the sky, and that spot shifted exactly 4 minutes each day. 4 minutes per day. That's the difference between solar time and sidereal time. The noise source wasn't turning with the sun, it was turning with the stars. The interference Jansky tried to eliminate turned out to be the voice of the Milky Way itself, a radio signal from the very center of our galaxy. This invisible signal carried information about processes no optical telescope on Earth could ever detect. This is how radio astronomy was born. Not from a theoretical breakthrough, not from an expensive expedition, but from an annoying crackle in the antenna. Over the next 2 decades, radio telescopes began scanning the sky methodically, and they found something that made astronomers uneasy. Point-like sources of radio waves, bright, sharp, compact, like stars, but only in radio frequencies. When astronomers aimed the most powerful optical telescopes at these points, there was nothing. Empty space. No stars, no nebulae, no galaxies. The radio waves shouted, "Something's here!" But the visible light said, "There's nothing here." That's when a paradox emerged, one that left astronomers completely baffled. Option 1. These objects lie nearby, within or close to our galaxy. In that case, their energy isn't mysterious at all. But if they are close, why hasn't a single optical telescope spotted them? Any object powerful enough to register in radio waves should glow at least faintly in visible light. It's like hearing a roaring engine behind a wall, but opening the door to find an empty room. Option 2. They're far away. Really far. Right at the edge of the observable universe. That would explain why we can't see them in visible light. They're just too dim at such distances. But here's the catch. For objects that distant to emit such intense radio signals, they'd have to release energy unlike anything produced by known physics. Not nuclear fusion in stars, not a supernova explosion, not even colliding galaxies. Nothing can account for that kind of brightness. Both options led to dead ends. Getting close was impossible. Going far was even more impossible. Let's be honest. In science, these moments are often the most valuable. When every explanation seems equally absurd, it rarely means the data is wrong. It means there's a gap in our understanding of the world. And in this case, that gap was enormous. No one had yet figured out how to measure it. Radio astronomers knew the coordinates of mysterious points in the sky, They knew their frequency, their power, and their steadiness, but they had no idea what exactly was shining there. To solve the mystery, they needed to pinpoint at least one source with enough precision to aim an optical telescope. Yet, the radio telescopes of the 1950s could only narrow down positions to within about a degree. That's like trying to find a specific house in an unfamiliar city when all you know is the neighborhood name. They needed a clever trick, a way to dramatically narrow the search area, and they found it in the most unexpected place. Every night, right overhead, moved the perfect tool for this job, huge, round, with a sharply defined edge. No one had ever thought to use it as a shutter before. The Moon. Astronomers Cyril Hazard and John Bolton, working at the Parkes Observatory in Australia, predicted that in 1963, the lunar disk would pass directly over the coordinates of the radio source 3C273. The idea was brilliantly simple. A radio telescope can't pinpoint exact coordinates because its beam is too wide. But if something with a perfectly known edge slowly drifts between the antenna and the source, the problem solves itself. The moon moves across the sky with a precision honed by centuries of observation. When its edge covers the radio source, the signal cuts out. When it moves away, the signal returns. 2 moments, 2 recorded times, 2 coordinates. The accuracy? Just a few arc seconds. It's like sliding your hand slowly in front of a candle and, by noting exactly when the flame disappears and reappears, pinpointing the candle's position to within a millimeter. Only instead of a hand, it's a rocky sphere 3,500 kilometers in diameter. This tool passed overhead every night, and it took years before someone figured out how to use it. The coordinates were precise enough to point an optical telescope at the spot. There, in that patch of sky, they found a faint bluish star of the 13th magnitude, dim, unremarkable, blending in with thousands just like it. It seemed the mystery was solved. The radio source was simply a strange star within our own galaxy. But then something happened that shattered the very foundation of astrophysics. Martin Schmidt, a Dutch astronomer working in California at the time, aimed a spectrograph at that little star. A spectrograph is basically a prism. It breaks the light from an object into its component colors. Within that rainbow, dark lines appear, fingerprints of chemical elements. Hydrogen leaves a line in one spot, helium in another, oxygen in a third. It acts like a barcode, revealing the object's composition, temperature, and speed. Each element has its own precise position. Schmidt examined the spectrum of 3C273 and found lines where they shouldn't have been. They didn't match any known element. For weeks, he sifted through every possibility. An unknown element, a calibration error, exotic physics. Then, right here is where everything changes. The numbers suddenly took on a whole new meaning. Schmidt did something simple. He shifted the familiar hydrogen pattern 16% toward the red side of the spectrum. The lines matched. Every single one. 16% redshift. In other words, the light from this object stretched 16% toward longer wavelengths during its journey to Earth. And in an expanding universe, redshift directly relates to distance. The farther an object is, the faster it moves away, and the more its light stretches. 16% meant a speed of about 47,000 kilometers per second moving away, and a distance of 3.4 billion light years. 3.5 billion years. The light that Schmidt split into a spectrum in his California lab left its source long before the first multicellular life appeared on Earth. It traveled to us across the planet's entire geological history, from ancient oceans to dinosaurs, from dinosaurs to humans. At that time, it was the most distant object known to science, the farthest one, and still bright enough to spot through a telescope. And here lies the biggest mystery. Not that the object is far away, but that at such a distance we can see it at all. An analysis of the brightness changes of object 3CE273 revealed something alarming. its brightness shifted over weeks, sometimes even days. Physics sets a strict rule. An object can't change brightness significantly faster than light can cross its diameter. If brightness changes in a week, the source can't be larger than 1 light week across. That's tiny on a cosmic scale. The size of this source matched roughly the span of our solar system, from the Sun out to Pluto's orbit, to put it simply. A region big enough to hold all our planets, all our asteroids, everything we know. And this region, a tiny speck by galactic standards, shone brighter than entire galaxies, brighter than hundreds of billions of stars combined. Something the size of our own backyard in the cosmos outshone entire star cities. No known physical process could explain it. Nuclear fusion? Too weak. Matter annihilation? Not enough mass. Nothing in the physics toolkit of the 1960s could produce that kind of power on such a scale. But the discovery had already happened, and the scientific community responded accordingly. Time magazine put Martin Schmidt on its cover in 1966. They compared the scale of his discovery to what Galileo achieved when he first pointed a telescope at the sky. That comparison wasn't random. Galileo revealed that the universe was larger than anyone had imagined. Schmidt showed it was brighter, more powerful, and stranger than anyone had ever dreamed. All that was left was to name these objects. In 1964, astrophysicist Hong-Yi Chu published an article in the journal Physics Today, introducing a term that quickly became one of the most recognizable in science. Quasi-stellar radio source was a mouthful. Chu shortened it to just one word: quasar. Short, sharp, and easy to remember. The word caught on instantly, in scientific papers, newspaper headlines, even dinner table conversations. It sounded almost like something out of science fiction, yet it described an object that surpassed any fiction in every way. Science uncovered a new class of objects. Names, positions, distances, brightness, size, all mapped out. But there was still one simple question without an answer. What physical mechanism could unleash the energy of an entire galaxy from a region no larger than a planetary system? Compact, insanely powerful, and stable for millions of years. Something hid at its core an engine unlike anything found in any textbook. The first surprise nobody saw coming didn't involve energy or size. It had everything to do with time. The farther astronomers found quasars, the further back into the past they were looking. 700 million light-years away, the closest. Beyond that, billions. Even farther, at the edge of the observable universe, just hundreds of millions of years after the Big Bang. Scientists reached a conclusion that flipped the whole search upside down. Quasars aren't stars within our galaxy. They are incredibly distant objects, typical of a young universe. Not the one we live in today, but one that vanished long ago. Simply put, each quasar is like a postcard from a time when the universe was just a few billion years old. We see them as they were back then. Their light has traveled longer than Earth has existed. That means quasars aren't just distant objects. They are ghosts, traces of powerful forces that raged in the young universe, but somehow stopped. Nearby, in the modern cosmos, quasars are almost nowhere to be found. Where they disappeared to is a question we'll get to later. While astronomers were still sorting out the time frames, the catalog of anomalies kept growing. And here's the fascinating part. These new objects didn't fit into any known category. A quasar is a radio source, discovered by its radio waves, identified by its radio emission. It made sense to assume that all these cosmic giants would shout in radio frequencies. But nature doesn't have to follow our logic. Alongside classic quasars, astronomers found a completely different class of objects, blazars. They didn't emit in radio waves. Instead, they shone bright and piercing in X-rays. The energy scale was the same, the absurd level of brightness identical, but the signature, totally different. It's like discovering two fires of equal power, one burning orange, the other invisible ultraviolet. The fire is the same, the flame is different. And that made people wonder, Maybe a quasar is just one face of something much bigger? The answer came from an unexpected place. Not from fresh observations of the 60s, but from archival data 3 decades old. Back in 1939, radio astronomers detected a powerful radio source in the constellation Cygnus. They named it Cygnus A. At the time, no one knew what it was, just a bright spot on the radio map of the sky. Years passed, technology improved, and when they finally took a closer look at Cygnus A, with new telescopes and sharper resolution, they saw something that left an entire generation of astrophysicists speechless. It was a galaxy. A whole island of stars, hundreds of billions of them. But not an ordinary galaxy. Its core blazed with an abnormal brightness, as if someone had switched on a spotlight in the heart of a city. From that core, 2 jets shot out in opposite directions. Streams of superheated matter accelerated to nearly the speed of light. 2 needles of pure energy piercing the void. The scale of these jets is something you have to feel to grasp. Our galaxy, the Milky Way, spans about 100,000 light-years across. The jets of Cygnus A stretch out for hundreds of thousands of light-years, each one in a single direction. Imagine 2 beams shooting out from the center of New York City, and each beam reaching not just the city's outskirts, or even the neighboring state, but all the way across the entire opposite hemisphere. But here, we're not talking about miles or kilometers. These distances dwarf entire galaxies. A structure born from the core of a single starry island turns out to be larger than the island itself. And here's where it gets even more astonishing. Quasars are monstrously bright points of light, visible across half the universe. Blazars are their X-ray counterparts, operating at a different frequency. Then there's Cygnus A, a galaxy with a spotlight core and jets piercing through intergalactic space. 3 distinct phenomena, 3 different names, 3 unique stories of discovery. Yet one detail unites them all. Their energy source always lies in the same place, right at the center, deep within the heart of the star system. Scientists coined a special term to describe this family: active galactic nuclei. These are galaxies whose cores shine brighter than all their stars combined. Not just dozens or thousands of stars, every star in the galaxy. Hundreds of billions of stars pale in brightness compared to a single point at the center. This term brought together quasars, blazars, radio galaxies, and dozens of other subtypes into one unified class of cosmic phenomena. Different masks, one actor. So the question stopped being simply, what is a quasar? Instead, it shifted to, what's happening at the heart of galaxies? What kind of process can outshine 1 trillion stars and hurl matter across distances larger than entire star systems? And here's a detail easy to miss, but impossible to ignore. Our own Milky Way has a center too. It's quiet, calm, no jets shooting out for hundreds of thousands of light years. But it's a center, and there's something there. They discovered this something in 1974. Not with an optical telescope. Visible light can't pass through the thick clouds of dust shrouding the center of our galaxy. Instead, they used radio antennas. 2 astronomers, Bruce Ballack and Robert Brown, pointed their receivers toward the constellation Sagittarius and caught a compact, bright radio source. A pinpoint. Completely still. Sitting exactly where calculations predicted the gravitational center of the entire Milky Way should be. They named it Sagittarius A. The signal stayed steady. The coordinates never shifted. But its nature? Totally mysterious. To uncover what was behind that radio signal, scientists didn't just listen to the source itself. They focused on watching what was happening around it. In the 1990s, 2 independent teams took on this challenge. One was in Germany, led by Reinhard Genzel. The other was in California, led by Andrea Ghez. Both teams began tracking the movement of stars near Sagittarius A star. Not just one star, but dozens. Year after year, frame by frame, they recorded their positions with incredible precision, down to thousandths of an arcsecond. It took more than 15 years, and the stars were moving. Not slowly, Not with the majestic pace you'd expect for stars in a galaxy. They were racing. One star, labeled S2, completed a full orbit around an invisible point in just 16 years. 16 Earth years for a full orbit. To put that in perspective, our Sun takes 230 million years to make one trip around the center of the Milky Way. S2 was circling that point 14 million times faster. At the point in its orbit closest to the center, its speed reached about 7,600 kilometers per second. That's 2.5% of the speed of light. At that speed, you could cover the distance from New York to Los Angeles in just 1 second. And this isn't a particle, not a photon. It's an entire sun, a blazing ball of plasma, hurtling as if shot from a slingshot. At the heart of this wild carousel, nothing visible. No glow, no disk, not the faintest optical trace. Just gravity. Pure, raw, silent gravity. Calculating the mass from the orbits gave one number, about 4 million times the mass of our Sun. 4 million suns packed into a space smaller than Mercury's orbit. What could weigh as much as 4 million suns and still shine no light at all? Imagine this thought experiment. Right now, about 26,000 light-years away, at the very point around which the entire Milky Way spins, every star, every planet, including Earth, including this exact square meter where someone might be sitting, there's an object capable of swallowing an entire star. Not just a theory, not some prediction on paper, real, with a measured mass, calculated coordinates, and a mapped zone of influence. It doesn't shine. It doesn't shoot jets stretching hundreds of thousands of light years. It doesn't spew plasma into intergalactic space. It just sits there, like a beast, full and asleep. In 2022, we finally captured its portrait. The Event Horizon Telescope Project, a network of 8 radio observatories stretching from Hawaii to the South Pole, operates in perfect sync, forming a single antenna the size of an entire planet. They gathered enough data to reveal something that had only lived in equations before, an image of Sagittarius A star. What you see is a blurry orange ring of superheated plasma swirling around a dark spot. A shadow, not the object itself, which is by definition invisible, but its silhouette, carved out from its own blazing surroundings. Gas hurtling at nearly the speed of light outlines the boundary of a void, from which nothing escapes. No light, no radiation, no information. That shadow measures about 52 micro-arcseconds across in our sky. That's like trying to spot a bagel resting on the surface of the moon. And yet, they did. Here's the detail that changes everything. Sagittarius A is quiet. Compared to quasars, which can outshine 1 trillion stars, our galaxy's central object is barely noticeable. It consumes matter in tiny amounts. Its true brightness is just a fraction of what it could theoretically achieve if it were running at full power. This isn't a spotlight piercing across the universe. It's a smoldering ember. But its very existence, right at the center of a calm, unremarkable spiral galaxy, rewrote everything we thought we knew. If an object like this sits here, in our own backyard, why wouldn't every galaxy have one at its core? And if quasars are blazing hearts devouring matter at monstrous speeds, and Sagittarius A is a core that barely eats at all, then the difference isn't in their structure, not in their nature, not in their physics. The difference is appetite. The mechanism is the same. Ours is just full. For now. And right there, in that pause, lies the greatest unease. The very same engine that turned distant galaxies into blinding beacons visible across half the universe beats at the core of our own home. It's alive. It's real. It's just dormant. For decades, physicists refused even to talk about this engine because the only explanation that fit the data felt like pure mathematical nonsense. It's 1916. Karl Schwarzschild lies in a field hospital on the Eastern Front. His skin is blistered from an autoimmune disease that will claim his life in 5 months. Between bouts of pain, he picks up a pencil and starts solving Einstein's equations, the very ones published just weeks earlier. Then he discovers something neither he nor Einstein expected. An exact solution showing that if you compress mass into a small enough space, the fabric of space itself collapses around it. Light can no longer escape. A boundary forms, a point beyond which nothing can be seen, measured, or retrieved. Schwarzschild sent his manuscript to Einstein from the front lines. Einstein presented it to the Prussian Academy of Sciences. For nearly 50 years, the physics community dismissed this solution as a mere mathematical curiosity, a beautiful formula disconnected from reality. Because an object with infinite density at its core? That was absurd. Nature doesn't work that way. The idea didn't appear out of nowhere, nor did it fade away. It smoldered for decades, with each new generation of physicists adding their own layer. In 1939, Robert Oppenheimer, yes, the very same, along with Hartland Snyder, demonstrated that a massive star, after burning through its fuel, could indeed collapse completely. In the 1950s, John Wheeler, who actually coined the term black hole, tried to organize the physics behind these objects. Then, in 1964, a groundbreaking idea emerged that tied everything together. These objects, collapsars, singularities, holes in the fabric of space, might be the engines powering quasars. Those dazzling points at the edge of the observable universe, shining brighter than entire galaxies. And they rejected this idea, not because the math was flawed. The concept of black holes, predicted by Einstein's general theory of relativity, just seemed too strange, too far removed from anything you could touch, measure, or capture on photographic plates. The equations were fine, but an object with infinite density at its core? No thanks. Then, the X-ray spoke up. The year is 1972. The Uhuru satellite, the very first orbital X-ray observatory, detects a powerful source of high-energy radiation in the constellation Cygnus. This source gets labeled Cygnus X1. Ground-based telescopes aim at the same spot in the sky and spot a blue supergiant, a massive, blazing hot star. But it acts strangely. Its spectral lines shift rhythmically, sometimes toward the red, sometimes toward the blue. It's wobbling. Something invisible, yet incredibly heavy, is making it spin, as if tied to a rope. Calculations show that this invisible companion weighs at least 10 times the mass of our Sun. Yet it emits no light in the visible spectrum. Nothing, not a single glimmer. But in X-rays, it shines with an intensity only matter heated to millions of degrees can produce. Gas streams from the surface of a blue supergiant, spiraling around this unseen object, speeding up and heating until it vanishes forever. The very compact source, once just an abstract point in early models, finally found an address. And that address pointed not to a star, but to a singularity. It seemed like the case was closed. Here's the object, here's the data, here's the mass. What else could you possibly need? It turned out, a bet. In 1974, Stephen Hawking, then 32 years old, made a wager with American physicist Kip Thorne. They put the bet in writing, both signing the agreement. Hawking bet that Cygnus X1 was not a black hole. Thorne took the opposite side. The stakes? The loser would buy the winner a year's subscription to a magazine. Hawking chose Private Eye, a satirical weekly. Thorne went with Penthouse. Physics was serious business, but their sense of humor stayed intact. Stephen Hawking later explained his stance like this. He wanted to lose. If Cygnus X1 turned out to be a black hole, it would mean his own theoretical work on the properties of black holes had real physical meaning. And if it wasn't, well, at least he'd get a consolation prize in the form of a journal subscription. But behind the joke was something deeper. One of the greatest theoretical physicists on Earth publicly doubted the reality of objects he had mathematically described himself. He held that position for 16 years. 16 years passed as data kept piling up. The mass of the unseen companion became more precise. Alternative explanations, a neutron star, an exotic white dwarf, fell one after another, unable to withstand the test of numbers. Then, in 1990, Hawking admitted defeat. Kip Thorne finally got his subscription. This moment is no joke. It's a turning point. When a mind like Stephen Hawking publicly admits, "I was wrong," the scientific community hears something clear. The debate is over. Black holes are real. Period. And that's when a door opened. A door that had been firmly shut before. If stellar mass black holes, like the one hiding in the Cygnus X1 system, exist, then the model scales up. 10 times the mass of our sun, that's the collapse of a single star. But what if these objects merge together? What if they swallow surrounding gas, grow, and merge over billions of years? Confirming the existence of stellar mass black holes strengthened the idea that supermassive black holes, sitting at the centers of galaxies and weighing millions or even billions of suns, form exactly this way, through merging and constant feeding on matter. From the corpse of a star to an object commanding an entire galaxy, a chain that begins with the death of one star and ends with a structure shaping the fate of trillions. Schwarzschild's mathematical curiosity, sketched with a pencil in a field hospital, turned out to be the blueprint of a real mechanism. The equations didn't lie. Nature really works this way. It just took physicists 74 years to accept it. And within that acceptance lies the true strength of the scientific method. Facts outweighed intuition, data overcame prejudice, and the bet was fairly lost. One question remained. If a black hole is a trap that lets nothing escape, where does the light come from? How does falling matter transform into the brightest radiation in the universe before vanishing forever? The story begins with debris, literally. Gas, dust, fragments of torn-apart stars. Anything close enough to a supermassive black hole starts to fall inward. But here's the key. It doesn't fall straight down. This isn't a rock dropped into a well. Every gas cloud, every shard carries its own sideways motion, angular momentum. As gravity pulls this matter inward, the physics of rotation stops it from plunging straight away. Instead, the material spirals. Layer by layer, stream by stream, gas, dust, and stellar remnants twist into a flat, rapidly spinning disk around the black hole, an accretion disk. This isn't a metaphor or poetic image. It's a real structure, a plasma pancake thousands of miles thick and wide enough to stretch beyond Neptune's orbit. The analogy here is almost embarrassingly simple. When water drains from a sink, it doesn't plunge straight down. It spirals into a vortex. Matter around a black hole behaves exactly the same way, but instead of water, it's superheated plasma. Instead of a drain, there's an object that lets nothing escape. And instead of lasting just a few seconds, this process goes on for millions of years. And this is where the real mystery begins. How does an object defined by the absence of light produce a glow brighter than 1 trillion stars? The key is friction. The inner layers of the disk spin faster than the outer ones. Between them, a fierce, viscous resistance builds up, layer rubbing against layer, plasma slowing down and heating up. The gravitational potential energy, the very energy of falling, doesn't just vanish. It transforms into heat, and not some mild warmth. The inner regions of the accretion disk blaze at tens of millions of degrees. At these temperatures, matter emits mostly ultraviolet and X-ray radiation, frequencies invisible to the human eye, but packed with immense energy. Simply put, the light from a quasar doesn't come from inside the black hole. It forms outside, in the last spirals of matter falling in, just before it crosses the event horizon and vanishes forever. A black hole isn't a lantern. It's a dark funnel, and the light comes from everything falling into it. And the power of this cosmic lantern is astonishing. The accretion disk converts up to 40% of the rest mass of matter into radiation. By comparison, nuclear fusion at the sun's core squeezes less than 1% out of hydrogen. That's a difference of tens of times. But the disk is only half the story. Spinning charged plasma generates an incredibly powerful magnetic field. The field's force lines cut through the disk, twisting and intertwining. Then, at a critical moment, some of the matter doesn't fall into the hole. Instead, the magnetic lines grab hold and sling it outward, perpendicular to the disk's plane. Up and down at the same time. Two narrow jets of scorching plasma burst from the system's poles, like twin spotlights aimed in opposite directions. The particles in these jets travel at nearly the speed of light. More precisely, 99.9% of light speed. Here, a mechanism operates that physicists once thought impossible. According to a model proposed by Roger Blanford and Roman Znajek, the jets don't draw their energy from the disk around the black hole. Instead, they tap into the black hole's own rotation. A spinning black hole twists the fabric of space-time around it, in a region called the ergosphere. This twisting transfers energy to magnetic fields, which then accelerate particles to relativistic speeds. Simply put, the fabric of reality winds around the black hole like thread on a spindle. This distortion then hurls matter back into space with an energy that's hard to comprehend. Pause for a moment. An object that nothing can escape from gives off energy, not from itself, but from the very geometry of the space around it. It's not matter fleeing the trap. The twisted fabric of space, warped by rotation, acts like a particle accelerator the size of our entire solar system. There's something almost musical about it, a precise mathematical elegance guiding a process that looks like pure chaos. Now consider the scale of the impact. These jets don't stop at the edges of their galaxy. They cut straight through it and push on. For hundreds of thousands of light years, even millions. A stream of plasma, born in a region the size of the solar system, pierces the vast emptiness between galaxies and heats the gas in entire clusters, massive structures holding thousands of star islands. It's like a single candle flame warming the air of an entire city. But the city stretches across tens of millions of light years, and the candle is no larger than a pinpoint on its map. Hot gas in galaxy clusters isn't just an abstract idea. X-ray telescopes actually see it glowing. It can't cool down and collapse into new stars because jets constantly pump energy back into it. Here's how it works. Friction in the disk produces radiation. Magnetic fields launch jets, and those jets heat the surrounding space far beyond the scale of any single galaxy. One point at the center, and its effects ripple out millions of light years in every direction. This is the full picture. An object no larger than Earth's orbit controls the energy balance of a space housing thousands of galaxies. Not through magic or some mysterious force, but through friction, magnetism, and the geometry of warped space. Three mechanisms, each understandable on their own, combine to create the most powerful engine in the universe. This machine converts matter into energy with chilling precision. But it has one limitation that defines everything. It needs fuel. And fuel, it's a given. For decades, astronomers built catalogs of active galactic nuclei and got lost in their own classifications. Seyfert galaxies of the first type, Seyfert galaxies of the second type, blazars, quasars, radio galaxies. Each new object seemed to demand its own category, different spectra, different brightness levels, different behavior in radio and X-ray wavelengths. The logical assumption was that each type had its own mechanism, its own physics, its own engine. And then the strangest thing happens, because there is only one engine. Take a simple flashlight. Shine it right into your eyes, a dazzling point of light. Step to the side, you see the cone of light and the body of the flashlight. Now move behind it. Just a dark cylinder, almost nothing. 3 observers, 3 descriptions. One calls it a star, another says a spotlight, the third, a piece of metal. All 3 are right, and all 3 describe the same object. The unified model of active galactic nuclei works exactly like this. An accretion disk, a torus of dust and gas and 2 jets, one structure. But if a jet points straight at us, we see a blazar, a dazzling point with variable brightness. If we look at an angle to the disk, it's a quasar, and if the torus blocks the center, we see a Type II Seifert galaxy. In other words, decades of taxonomic confusion boil down to one question: at what angle are we looking? It's elegant, but behind that elegance hides a troubling truth. If quasars, blazars, and others are essentially the same kind of object, then why don't we see quasars nearby? We only detect them billions of light years away, and billions of light years means looking billions of years into the past. So quasars aren't just distant, they're ancient. They belong to a different era. That's where the real mystery begins. Or rather, the answer, which turns out to be sadder than any mystery. A quasar is a machine that converts matter into light, but every machine needs fuel. For the accretion disk to burn, it requires a steady flow of gas. Where does this gas come from? From collisions. When two galaxies draw close and merge, gravitational tides strip gas clouds from their orbits, funneling them straight into the black hole's maw. Billions of years ago, in the early universe, galaxies huddled closer together. The distances between them were smaller. Collisions were more frequent. Gas was abundant. The conditions for quasar activity were perfect. Then the universe expanded. Galaxies drifted apart. Collisions became rare. Gas grew scarce. One by one, quasars faded. Not because their engines broke down, but because they ran out of fuel. This is the answer we hinted at earlier. Quasars didn't vanish in some cosmic disaster. They simply went hungry. Now, look up at the night sky. Quiet. Calm. The stars twinkle softly. The Milky Way stretches across as a faint band. Nothing gives away that here once raged a fire fierce enough to outshine an entire galaxy. Today's cosmos feels like a concert hall after the show has ended. The seats are still in place, the lights are dimmed, and the echoes have long since faded. Most supermassive black holes in nearby galaxies are asleep. They remain massive, millions, even billions of times the mass of our sun, but there's no gas, no disk, no jets around them. Silence. Our own giant, Sagittarius A star, at the heart of the Milky Way, is asleep too. 4 million times the mass of the sun, yet almost no activity. A faint, barely noticeable radio source. But here's the fascinating part. In 2010, the Fermi Gamma Ray Space Telescope discovered something completely unexpected. 2 enormous bubbles of gamma radiation positioned exactly perpendicular to the plane of our galaxy. One above it, the other below. Each bubble stretches about 25,000 light-years from the center. Together, they span 50,000 light-years of pure energy, hanging in space like 2 ghostly wings. The data had been there all along. The signal appeared in earlier observations, but only after scientists subtracted all known sources of gamma radiation, galactic dust, cosmic rays, pinpoint sources, did these structures emerge from the noise. Massive, symmetrical, unexplainable by anything except one thing: jets. Remnants of powerful emissions that once burst from the center of the Milky Way, back when Sagittarius A star was still awake, when our galaxy was ablaze. Simply put, the Milky Way went through its own quasar phase. We live inside a former quasar. The Fermi bubbles aren't an active event. They're a scar, a mark left by a wound that healed millions of years ago. The gas has long since vanished, the jets have faded, and the black hole has fallen asleep. But the structures it left behind still glow in gamma rays, like the embers of a fire long extinguished, with the ground beneath still warm. When you look at it this way, at the bubbles, the dormant cores, the galaxies drifting apart, a clear picture emerges. It's hard to look away. The universe is growing old. Its wild youth, full of collisions and fire, lies behind us. We were born in an era of silence, on ashes, among cooling giants that once blazed brighter than 1 trillion stars. If quasars are a feature of the young universe, one question still haunts us. The most distant quasars appear at a time when the cosmos was less than 1 billion years old. Yet, the the black holes at their centers already weighed billions of times the mass of our sun. Where did they come from? How did something so massive grow so fast? If we were talking about just one strange object, we might chalk it up to an observational error, noise in the data, a calibration glitch, a random spike. But today, astronomers have cataloged over 1 million quasars. 1 million. That's more than the population of a city like Cleveland. And that counts only those we've managed to detect and log in databases. Estimates put the total number of quasars in the observable universe at around 10 million. Each one harbors a supermassive black hole at its core. Each is surrounded by an accretion disk, heated to millions of degrees. This isn't an anomaly, it's a pattern, and patterns demand explanation. The deeper telescopes peer into the past, the sharper one question becomes. The farthest known quasar goes by the catalog name J0313-1806. Its light traveled more than 13 billion years to reach us. This object existed when the universe was only 670 million years old, about 5% of its current age. Imagine compressing the entire history of the cosmos into a single day. This quasar would blaze into view a little after 1 in the morning. And by that time, the black hole at its core already weighed 1.5 billion times the mass of our sun. Not a million, not 10 million, 1.5 billion. All this in a baby universe where the first galaxies were barely even taking shape. How did it gain so much mass in such a tiny span of time? To understand why this number causes astrophysicists almost physical discomfort, we need to look at one key mechanism. A black hole grows by swallowing the matter around it. Gas spirals inward, forming an accretion disk that heats up to extreme temperatures through friction. As the gas loses energy, it falls past the event horizon. The black hole's mass increases. But this process has a hard limit, the Eddington limit. The physics behind it is straightforward. The more gas falls onto the black hole, the brighter the accretion disk shines. At some point, the radiation pressure becomes so intense that it pushes the falling matter away. It's like trying to pour water into a bucket with a fountain shooting out. The harder you pour, the more water sprays back. There's a maximum speed at which a black hole can gain mass, and exceeding this speed would break fundamental physics. Now, let's talk numbers. Take a typical stellar black hole, say about 10 times the mass of our sun, and let it grow at the maximum possible rate, continuously, without stopping, for 670 million years. Even then, it wouldn't reach 1.5 billion solar masses. The standard growth model, through mergers and steady accretion, just doesn't cut it. There isn't enough time, or more precisely, not enough cosmic budget. To reach the observed masses, the black hole would have had to start growing before the universe itself existed. The math just doesn't add up. So what's the logical next step? Look for intermediate stages. If you can't grow a monster from a single tiny seed, maybe many medium-sized seeds merge together, speeding up the process? Intermediate mass black holes, ranging from 100 to 100,000 solar masses, would be the perfect candidates. A ladder nature climbed, stepping up from stellar black holes to the giants we see today, skipping rungs along the way. But we don't see this cosmic ladder in action. Objects of intermediate mass are incredibly rare. Between stellar black holes weighing 10 to 20 times the mass of our sun and the giants tipping the scales at millions or even billions, there's a yawning gap. It's like walking into a natural history museum where you find only a mouse skeleton and an elephant's, and empty display cases in between. No cats, no dogs, no horses. The missing link between these two classes of objects simply isn't there. And that doesn't just make the picture confusing, it makes it downright puzzling. It's as if nature never climbed the steps, but leapt over several flights at once. When conventional physics hits a wall, bold new ideas step into the spotlight. Ideas that just a decade ago would have seemed too daring for peer-reviewed journals. The first hypothesis: a direct collapse of dark matter clouds. In the early universe, when ordinary matter was scarce, Massive clumps of dark matter could have collapsed straight into black holes, weighing tens of thousands of times the mass of the Sun, skipping the entire star phase. No stars, no supernova explosion, just a ready-made black hole with a hefty head start. The second idea. The first generation of stars, known as population 3 stars. These weren't your typical stars like our Sun, but giants hundreds of times more massive, made almost entirely of hydrogen and helium, with no heavy elements. They would have burned with fierce intensity, lived only a few million years, and then collapsed into black holes already carrying significant mass, primed to grow even larger. The third hypothesis is the most radical: primordial black holes. These are objects that didn't form from stars or gas clouds. Instead, they emerged directly from density fluctuations in the first fractions of a second after the Big Bang. If the infant universe contained regions dense enough, they could have collapsed in on themselves before space even had time to expand. John Wheeler once remarked, "A black hole has no hair," meaning it doesn't matter what it formed from. If primordial black holes exist, they would be indistinguishable from any other black hole. That's exactly why proving their existence is so challenging. None of the three theories has yet received conclusive observational proof. None has been disproven either. The James Webb Space Telescope is already capturing photons that traveled more than 13 billion years to reach us, light from the very era when these impossible objects somehow already existed. We still don't have an answer, but the lack of one isn't a dead end. It's a signpost. Something fundamental in our models of the early universe is either incomplete or wrong. And there's one pattern that looks even stranger than the rapid growth itself. The mass of a supermassive black hole and the mass of its host galaxy are linked so tightly they seem to have grown from the same blueprint. It's as if the monster at the center didn't just live inside the galaxy, it somehow set the rules for its growth. Scientists discovered this connection around the turn of the millennium, and it turned out to be as unyielding as the law of gravity. The mass of a supermassive black hole and the mass of the galaxy's stellar bulge, the central thickening, correlate so precisely that chance seems impossible. Double the black hole's mass, and the bulge doubles too. The galaxy grows, and the monster at its heart grows alongside it. Not roughly, not by guesswork. According to a single blueprint, as if an invisible cable tied them together. But here's the fascinating part. The black hole occupies an insignificant volume within the galaxy. Literally just a pinpoint. If the Milky Way were Moscow, then the star Sagittarius A star would be like a coin resting in Red Square. So how can an object the size of a coin dictate the scale of an entire city? What kind of connection links the core to the outer edges, spanning tens of thousands of light years? Here lies a mystery that has puzzled astrophysicists for decades. They built models of galaxy evolution, ran computer simulations, and each time they got the same result. Galaxies in their models formed stars too quickly, absurdly fast. Gas would compress, cool, and collapse into new stars at such a pace that the galaxy should have burned out within just a few 100 million years. Like a match tossed into a barrel of gasoline. One flash, and it's all over. Darkness. But real galaxies live for billions of years. Our Milky Way has been shining for 13 billion years, and it's still creating new stars. Not at a frenzied pace, but steadily, a few at a time each year. Something was holding the process back. Something stopped the gas from collapsing into stars too greedily. They searched for answers where they should have, in the physics of interstellar space, magnetic fields, turbulence, and shock waves from supernovae. Each theory explained a piece of the puzzle, but none could fill the glaring gap in the calculations. Models stubbornly kept producing dead galaxies instead of living ones. Then, someone stopped looking at the stars and looked at the coin, at the black hole in the center. The mechanism turned out to be frustratingly simple. When galaxies collide, and in the early universe this happened all the time, massive clouds of gas rush toward the center of the merged system. The gas falls onto the supermassive black hole, accelerating to near-light speeds, heating up to millions of degrees. and the core bursts into life as a quasar. The very same quasar that shines brighter than 1 trillion suns. The same one we've long thought of as a force of destruction. A quasar's flare unleashes radiation so intense it heats gas thousands of light years away from its core. It doesn't destroy or evaporate the gas, it simply warms it up. Imagine a campfire not just heating the clearing around it, but raising the temperature across an entire national park. As the gas heats, it expands, its density drops, and that's when things get interesting. For a star to form, a cloud of gas has to collapse. Its own gravity must overcome the internal pressure, pulling the material into a dense clump that will eventually ignite nuclear fusion. But if the gas is hot, the pressure inside pushes back too hard. It resists collapse. Simply put, a hot cloud can't become a star. It's too stiff, too puffed up. It just hangs there in space, cooling off. Slowly, over millions of years. A quasar acts like a fuse in an electrical circuit. When the current gets too strong, the fuse blows and breaks the circuit, protecting the whole system from a short. When gas falls into a black hole too rapidly, a quasar ignites, heating the surrounding space and halting runaway star formation. The gas stops collapsing. New stars stop forming. The flow of matter into the black hole dries up. The quasar fades. The gas begins to cool slowly. Tens of millions of years pass, and the cycle starts again. But this time, it's gentler, calmer. The galaxy doesn't burn out all at once. It smolders for billions of years. That's why the mass of a black hole and the mass of its galaxy grow in sync. They're not just neighbors. They're parts of the same thermostat. The black hole controls how much gas turns into stars. The stars decide how much gas remains to feed the black hole. It's a feedback loop, self-regulation, a system that balances itself across cosmic epochs. Here's where we need to pause and grasp how big a mistake astrophysics made for decades. Quasars were discovered in the 1960s. For 50 years, scientists thought they were anomalies, cosmic disasters, meaningless outbursts of violence in the cores of distant galaxies. Textbooks called them the most destructive objects in the universe, and that was true. But the full truth was something else, more like the opposite. Destruction was actually the mechanism of preservation. Fury was the tool of stability. Without quasars, galaxies would have burned out like dry tinder. Without that blinding flash that seemed like pure chaos, there would be no spiral arms, no long-lived stars, and no planets orbiting them. And this hits close to home. Sagittarius A star, a quiet, nearly dormant black hole at the center of the Milky Way, was once a quasar. Billions of years ago, when our galaxy was younger and hungrier, its core blazed with a fury hard to imagine today. That fury heated the surrounding gas, slowing star formation. It stretched out the hydrogen supply for billions of years. And that's exactly why, 4.5 billion years after the quasar died down, a modest yellow star formed in a calm spiral arm from the remnants of that ancient gas. Around it, a rocky planet. On that planet, water. And in the water, the very first molecules capable of copying themselves. The past activity of Sagittarius A star as a quasar likely played a crucial role in preventing the Milky Way from burning out too early. It ensured there was enough gas. It kept the environment calm enough. It gave chemistry the time it needed to evolve into biology. We are a byproduct of an ancient fury. This delicate balance between bursts of light and stretches of silence, between the blazing core and the cold outskirts, has sustained our galaxy for 13 billion years. But gas supplies won't last forever. And just a few million light years away, in the constellation Andromeda, something is already moving toward the Milky Way, carrying its own core and its own hunger. 2.5 million light years separate us from Andromeda right now. It sounds like a safe distance, but Andromeda is speeding toward the Milky Way at about 110 kilometers per second. This isn't a guess or a theory teetering on the edge of uncertainty. It's a direct measurement confirmed by spectroscopy in the early 20th century and refined by the Hubble Space Telescope in 2012. In a few billion years, the Milky Way will collide with Andromeda. Two spiral disks, each packed with hundreds of billions of stars, will begin to pass through one another. Here's the strange part. Most stars probably won't collide with anything. The distances between them are so vast that when two galaxies pass through each other, it's like two swarms of fireflies drifting across a dark field, glowing but never touching. If the sun were a cherry, the nearest cherry would be 400 kilometers away. Star collisions during galaxy mergers are incredibly rare, but gas behaves differently. Gas crashes together, it compresses, it heats up, and it falls inward. Where exactly? Toward the center, to the place where Sagittarius now lies in quiet slumber, a star that is actually a black hole weighing 4 million times the mass of our Sun. Nearby, its Andromeda counterpart awaits, a black hole at the heart of the neighboring galaxy, 30 to 40 times more massive than ours. These two giants will begin to draw closer. Gravitational friction will tighten their orbits, pulling them into an ever closer dance until they merge into a single object. At the same time, trillions of tons of fresh interstellar gas, stirred up by their collision, will rush into this new core. The fuel returns. The accretion disk ignites. Jets pierce the surrounding space. The center of the newborn galaxy, what astronomers have already named Milkomeda, will flare into a quasar. For millions of years, the sky will flood with light this part of the universe hasn't seen since both galaxies were young. The cycle closes. The very same mechanism that, 13 billion years ago, stopped the young Milky Way from burning out completely will kick in again. A new burst of fury will sweep away the excess gas. A fresh flare will slow down star formation. This new destruction will lay the groundwork for a new kind of stability. And this is where we need to pause. We're used to dividing the world into two piles. One holds what builds: rain, light, growth, calm. The other holds what breaks: fire, impact, explosion, disaster. It's simple. It feels natural. But honestly, it just doesn't hold up on a scale that stretches beyond a human lifetime. A forest fire burning through the underbrush clears the ground for sequoia seeds. Without fire, sequoias don't sprout. A river flooding its valley deposits silt that will nourish fields for 1,000 years. These are familiar examples, but a quasar operates on the same principle, only magnified to a cosmic scale. It's an object unleashing the energy of 1 trillion stars, tearing apart gas clouds across thousands of light years. And yet, this same force makes it possible for the galaxy itself to survive long enough for life to emerge. If total destruction turned out to be a condition for our existence, what other catastrophes might we be unable to grasp in their true scale? Not because we lack data, but because we simply don't have enough time. 70, 80 years? That's our horizon. But the processes that shaped us have stretched across billions. We are observers shown a single frame from a film that stretches on forever, asked to guess its genre. The frame is dark, so we label it horror. But space has no genre. It has no villains or heroes, only a mechanism operating on a scale where our usual categories lose all meaning. The star Sagittarius A lies dormant. The Milky Way's gas reserves are slowly running dry. Andromeda is speeding closer, covering 110 kilometers every second as these words unfold. Someday, after a span too vast to truly feel, measurable only by numbers, the silence will break. The beast will awaken. The sky will ignite. And the ancient cycle of destruction and creation, the very cycle that once gave rise to us and our questions, will begin anew.